Okay, so let's get started with section 4.1. Oops. 4.1 is probability and odds. Probability and odds. Okay, so definition. Number 1, an outcome. That's our first definition. An outcome is the result of an experiment. So is the result of an experiment. Next definition will be an event. An event, which is what we're going to be dealing with in this section, is a particular slash group of outcomes. This will make more sense once we begin to apply it. The third definition will be a simple event. A simple event. That has a single outcome. So has a single outcome. And number 4, a sample space. Final definition, a sample space is all possible simple events. So next is a theorem. It's a terrible M. Theorem. So when all outcomes are equally likely, once again, this will make sense once we start doing examples. So when all outcomes are equally likely, the probability, call it capital P, of any event, and we'll call the event capital E, is given by so the annotation is the probability of event E, so P in parentheses, capital E, and it's going to be a quotient. On top is the number of outcomes corresponding to E, so number of outcomes corresponding to E, the event, all divided by the total number of all outcomes. So total number of all outcomes. Okay, so actually before I do that, let's note something. Yeah, let me use a different color. So let's note that the probability of event E is a percentage. And as such is a is a value between 0 and 1. That is, i.e. it est 0% and 100%, respectively. Okay, so finally, an example. So for example, let's find the probability. Find the probability of the following events. So number 1, let's have that be rolling a 3 on a die. So a die is the singular for dice. Okay, so what we're going to do is we're going to let capital E be equal to rolling a 3. So E, of course, is my event, and the event is rolling a 3. So the probability of rolling a 3 on a single die, well, remember, each die has 6 sides. So I know that the total number of sides is 6, but of those 6 sides, only one of them has a 3. So therefore, the probability of rolling a 3 on a die is 1 in 6. And notice that's less than 1. Okay, so let's do another one. So number 2. What's the probability of rolling an even number? So rolling an even number on a die. Number on a die. Okay, so in this case, we're going to let the event E be equal to rolling a 2, 4, or 6. Do you agree that each of those is an even number? So therefore, the probability in this case of the event happening will be, well, there's 6 total sides, but how many sides have an even number? Well, 3 of them, right? 2, 4, and 6. And of course, this reduces because 3 goes into 6 twice. So this reduces to 1/2. So it's a 50% chance that we'll roll an even number. And of course, a 50% chance we would roll an odd. So let's consider the probability of an event E in the case number 1, that E is certain to always occur. To always occur. Well, the probability of an event that is always going to occur is 1. That is 100%. Because if it's always going to occur, then there's a 100% chance it will always occur. Analogously, let's say E will never occur. Will never occur. Well, the probability of something that's never going to happen is 0, right? So I hope that intuitively makes sense. And let's note something. The probability of an event can never be greater than 100%. So the probability of an event can never be greater than 100%. That is 1. Okay. So pardon the cat. Let's also note the sum of the possibilities, or the sum of the probabilities of non-overlapping events. I should say of all non-overlapping events. Overlapping events is 1. So for example, the probability of getting an even plus the probability of getting an odd, well, each is 50% and their sum is always 1. So let me actually write that down. So for example, the probability of rolling an even number plus the probability of rolling an odd number so that's going to be, well, the probability of rolling an even number was 3 in 6. The probability of rolling an odd number is also 3 in 6. So we end up with 6 over 6, or 1. Let's also recall a bit of annotation. So recall, we had this little symbol, squiggly A, and that meant not A, right? Okay, so continuing on, definition. So the complement, that's what we're defining. The complement of an event, E, capital E, denoted by E with a bar over it, is the event that E doesn't happen. So we can think of it as something like E with the bar over it is equivalent to not E, in a sense. So let's make sure we note that there's a bar over the top of it. And let's also note that the probability of event E plus the probability of the complement to E. Let me do this in red like I did the not before, is always going to be 1 because they're non-overlapping events. So for example, find the probability of picking anything but a queen from a deck of cards. Okay, so what I'm going to do is I'm going to let E be the event picking a queen. Picking a queen. Okay, so what does that mean? That E with a bar over it, or not E, is the event not picking a queen. So I should probably write not in red. So not picking a queen, which is what we want to do. We want to not pick a queen in a deck of cards. Well, what do I know? I know that the probability of event E picking a queen plus the probability of the complement to E not picking a queen, that always sums to 1. So what is the probability of picking a queen? Well, do you agree that there are 4 queens? It's a terrible 4. Let me write that a bit better. There are 4 queens for every 52 cards in one deck, plus the probability of not E, which I'm trying to find, is equal to 1. Okay, so I know that the probability of not picking a queen, or not E, will be 1 minus 4 50-seconds. But do you agree that 4 goes into 52 13 times? So I can really write this as 1 over 13. That is, there's 1 queen in every suit of cards. So the probability of not picking a queen, or not E, is going to be 13 over 13 minus 1 over 13, leaving us with 12 over 13. So the probability, oops, wrong color, the probability of not picking a queen out of a deck, a single deck, is going to be 12 out of 13. And that should make sense because every suit has 13 cards, one of which is a queen. So of every suit, there are 12 cards that are not queens. So hopefully that makes sense logically. Okay, so let's consider let's do 1 circle. Trying to make it a circle. No, that's terrible. That's not a circle. Huh? Will that be a circle? Yes. So let's call this event A. And let's do another circle for event B. Event B. So these are distinct, independent events. So So independent, dependent events. Neither one depends on the other to happen in this illustration. However, what if I have the case of event A and event B where they do overlap? Oh, come on. Why is it so hard to draw a circle? So in this case, these are dependent events because they have an overlap. So this is dependent. Events. For example, an ace of hearts. It's both a heart and an ace, so it overlaps. So theorem. So let's let A and, what color should I use? B be two events. If A and B are independent, meaning they don't overlap, independent, then the probability of A and B, so that's a probability of A and B happening, will be the product. So it'll be the probability of A times the probability of B. Just need to take their product to find the probability of both occurring, provided they are independent. In the second case, if A and B are dependent, then the union P, the probability of the union of A and B, is going to be the probability of A or B. Actually, you know what? This one works either way. Thinking about it, will be the probability of A plus the probability of B. And if they are dependent, then I'd be required to subtract their intersection, which is where A and B intersect. So what do I mean by that? Wrong color? So for example, let's find the probability of picking an ace of hearts. How about that? So find the probability of picking an ace of hearts from the deck using the formula for the probability of A and B, their intersection. Okay, so in this case, we've got two events really. So let's let A be the event of picking an ace. So picking an ace. And let's let B be the event of picking a heart. What I'm looking for is the overlapping of these events. So I claim that the probability of picking an ace and a heart, all in one fell swoop, will, by definition, be the product of picking an ace and picking a heart. And let's see if that makes sense. Let's see if the math actually works. Well, the probability of picking an ace, so how many aces are there in 52 cards? Times the probability of picking a heart, how many hearts are there in 52 cards? So there are 4 suits, meaning 4 aces, in 52 cards. And there's a whole suit of hearts, meaning 13 out of 52 hearts. But these reduce. I know that 4 goes into 52 13 times. And similarly, 13 goes into 52 4 times. So what we end up with then is 1 over 13 times 1 over 4, which is 1 in 52. Okay. Now, does that make sense? Is there one ace of hearts in 52 cards? Yes, there are. So this formula works for that scenario. So let's do another one. So for example, so what is the probability? So what is the probability? The probability of picking an ace or a heart. So now I'm not looking for the ace of hearts, I'm looking for either an ace or a heart. So once again, let's let A be the event of picking an ace. Picking an ace. And let's let B be the event of picking a heart. So according to the formula above, the probability of picking A or B is going to be the probability of A plus the probability of B minus their intersection. So the probability of A plus the probability of B minus A and B. Okay, so let's think about this. What is the probability of picking an ace? Well, we know that there's 4 aces for every 52 cards. And what is the probability of picking a heart? Well, there's 13 hearts in 52 cards. And what was the probability of picking an ace of hearts? Well, from above, we know that that was 1 in 52. Okay, so what I get then is 4 plus 13 minus 1 all over 52. So that's going to be 16 out of 52. Is that true? 16 out of 52. And that does reduce if I care to, but I'm going to leave it here for just a moment and let's think about this. Picking an ace or picking a heart. I could choose from 13 hearts, and one of those is already an ace, so there's 3 aces left over. So 13 and 3 is indeed 16, so that does work. Okay, now we can go ahead and reduce. So 2 goes into 16 8 times, and it goes into 52, 26 times? So that's going to reduce again. 2 goes into 8 4 times, and 2 goes into 26 13 times. So interesting, it's over 13 again. So we have 4 out of 13 as the probability. So I hope this makes sense.